Hello everybody. Welcome to today's talk in modern database concepts. We will talk about spatial data. Yeah, say hello in the chat. Many people are there, that's very great. And yeah, what will we talk about today? Spatial data is basically part of the SQL standard SQL so a special substandard of the SQL language called multimedia. SQL stands for multimedia, and yeah, this standard standardizes working with text data, with image data, with geographical data as well. Can you upload the slides to this session? Yes, in 1 minute I will do so. Sorry that I forgot this. While I do this, I talk a bit about geospatial data. I could also talk about dates and timestamps. Why do we need a special type for date and timestamp? We have integer. So what many people do when they convert a date or a timestamp when somebody places an order into an integer value. I check my microphone. Sorry, now the microphone should be better. This time I realized it by myself, or was somebody? No, nobody wrote something into the chat. Yeah, you could write an integer when you store a timestamp value, the number of seconds since the 1st of January 1970, or so the Unix timestamp. Or for geographical data, when you want to store where does a person live, or where did a person use the mobile phone app, GPS coordinates, simply use two columns, longitude and latitude, and store decimal numbers there, the longitude and latitude values. Yeah, but for timestamps, you all know it's better to use a timestamp data type or a data type, because you can easily convert this into a formatted date, for example. Or you can easily extract the month or a year, or group several dates which belong to the same week into the same group, and so on. So you have many built-in functions in relational databases when working with these data types. And for geospatial data, it's the same. We have a special data type for storing longitude and latitude values, but not only that, the geospatial standard also offers more complex types, not only points on Earth, but also lines, line strings, areas, and so on, because not everything is a point. So into the lecture catalog, I now uploaded the PDF of this chapter, and so you can download it now. Okay, we will do some quizzes today, as you all know. So be prepared. Okay, let's begin. We start with talking about spatial data in general. So before we can introduce the data type and working with SQL with that spatial data, what is the spatial data? It is data that belongs to somewhere on the real world. For example, a customer lives here where this point is. yeah, this is basically represented by a point with an x coordinate and a y coordinate, longitude and latitude. But spatial data is also something like this. What is this? I don't know what this is. This can be anything geometrically. Oh, what happened with this? This can be anything in a Euclidean space, in a two-dimensional space or three-dimensional space. It can be maybe a CPU, a chip. So chip manufacturers, they can use spatial data to organize where is a transistor on a chip and so on, and then make computations and optimizations within the database there. Or this can be a room. Here are tables in a room and maybe chairs and so on. Or maybe this is a building, and within a building you have x and y coordinates, which have nothing to do with longitude and latitude, but simply to organize within a building or so. We will mainly focus on the left part here, representation of real-world objects. But everything that we do today, having a point somewhere with x and y coordinates, or having areas and line strings, also works without speaking about the Earth. Because basically this on the right side is much easier. So simply having a point somewhere with coordinate 0, 0, and then another point with 1, 1. Then you can simply compute the distance by Pythagoras. 1 squared plus 1 squared is 2, and then the square root of that is the distance between 2 points. This is very easy. And on the Earth it's much more complicated. Why is computations and calculations on the Earth so complicated? The reason for that is the Earth is not flat. The Earth is a globe. It's a ball. And yeah, you can simply pick two coordinates here, let's say here and here. They have very similar values in their longitude and latitude. But let's pick two values here on the North Pole. They can have very, very different values on the longitude and latitude. Okay, only one of them is very different. The latitude is this, and the longitude is this. So they can have on the North Pole the same latitude because they are very north, but they can differ a lot in the longitude value, and the distance is very small. So the challenge here is to project such a three-dimensional globe into a flat map. For cities like Regensburg, London, Berlin, this might be easy. So for locally, it's very easy. Even locally here on the North Pole or South Pole, it's easy. But to make this possible on the whole world, it's not so easy. So that's a challenge why this real world is the most complex one. The data that origins here or here in geospatial format, systems that work with these data are called geographic information systems. So an information system in general is a software that works with a database and stores something into a database, collects data, maybe it imports data from somewhere, or it uses sensors or human input or a web form. There's a website where people insert the data. So data is collected, stored in the database. Then at the other end, people analyze this data, make some computations, and they provide the data for everybody, or a limited number of people to access the data. Yeah, and the area of the Earth is what it's stored in such a geographic information system, also called GIS. Yeah, I talked about latitude and longitude, and I can never remember what is what. Yeah, maybe longitude, it's a long way when you want to travel around the Earth or so on. I don't know how to remember it. Maybe for you it's easier than for me. So longitude, we are currently, when we are in German, at longitude a very small number. I don't know, 7 or 8 or so, 6, don't know, 10. Yeah, not a large number, because the longitude 0 is at London, Greenwich, where Greenwich Mean Time also is, where the time zone 0 is the UTC time. There's also the GPS position, or the longitude 0, and the latitude 0 is is here at the equator. So here we have latitude 0, and then we go a lot on top. Then we have latitude up to 90, or we go south, then we have -90. And when we are in London, then we go either north up to 180 degree. If we go 180 degree in the longitude, then we are at the other side of the world, the opposite position to London. And if we go 180 in the west way, then we are at the same point. So basically this one point is the same, independent whether you go east or west. So, and that's also a problem. So let's say you go from London 179 in the east direction, and on the other day you go 179 on the other direction, on the west direction. Then you are almost at the same point, but a computation, or when you look at these numbers, would say, wow, this is very, very far away. So this has to be yeah, you have to be careful when working with these numbers. But yeah, there are already built-in functions which make it easier for you to not care about all these things, that the Earth is a globe, and the Earth is not really a ball, not really a perfect ball. It's an ellipsoid or something. So an ellipsoid is something like a ball, but it can be very flat. So if you flatten it down, then you almost have like a pizza, so with a round surface, or you move it in the long direction, so it's like an ellipse which goes three-dimensional. So that's like an egg. Yeah. And when we have these latitude and longitude values, I told you, we measure them, we use the unit of degrees. So for the latitude, we have 90 degrees when we are at the North Pole, 90 degrees north, or 90 degrees south, and 0, so it's between 0 and 90. And the longitude is between 0 and 180, either in the north, or either in the south, either in the west, or either in the east direction. So here we have degrees. We have to be remember that we work with degrees. So for now it should be very clear for you. Well, degrees, I know that. I saw GPS positions. When you go to Wikipedia, Regensburg, and you open the Wikipedia article, you see here the coordinates on the top, and I open it in the English Wikipedia. So here you see coordinates. It is very not very accurate. yeah, more accurate it would be when this 1 would have much more decimal digits, but Regensburg is not one point. Basically Regensburg or each other city is a bigger area, and this is, yeah, approximately 1 point within that area. So it's not in the center of Regensburg, not at the main station. They just chose this point because that point here has only a very small number of fractional digits. So 49 degrees in the latitude direction, so 49 degrees north. It's not 0, otherwise we would be at the equator, and it would not be south, otherwise we would be south of the equator. No, 49 degrees north, 90 would be the North Pole, and 12 degrees, okay, it's 12 in the longitude direction, so it's 12 degrees from London. When we look for London, we see here 0 degrees west. Okay. Yeah, and degrees is important. Degrees is also what a GPS sensor gives to you when you have a GPS sensor. Every mobile phone has GPS built in. Some smart watches have GPS built in, and they provide you longitude and latitude in degrees. Yeah, why is this so important? Because first of all, remember these problems I told you about when you're next to the North Pole or South Pole or on the other side of the Earth. Then you cannot simply say that two close together values are very close together on the Earth, and two values which seem to be very far away from each other can be very close together. Yeah, that's the problems. And another thing, when you compute with degrees, like with Pythagoras, I am here at Regensburg. That's what did we say? 49 in the x direction, in the y direction, and in the x direction 12 or something, or 10. And in London it was 0 and blah blah blah. You cannot simply use Pythagoras to compute a distance. Okay, you could do that, but it would be inaccurate, and you would get the distance not in meters or miles or yards or kilometers or so. You would get the distance in degrees. And what helps it to you when you have the distance between London and Regensburg in degrees? So the distance between London and Regensburg is 11 or 10 or something. Okay, what does this help? Then you have to maybe multiply this times the diameter of the Earth, 40,000 or so, and this is also not correct. So it is very hard to work with these numbers. So the challenge here basically is just the projection. If we would have an algorithm that projects our three-dimensional ball or ellipsoid into a two-dimensional space, then making computations on this two-dimensional space, on this map, would be much easier. There are many different projection algorithms, not just one, because one algorithm can be good for a very local area. So for example, there's one algorithm which maps the GPS positions within West Germany or East Germany into a map, and then we have there a good possibility to make distance computations and so on. And another algorithm is good for South America and so on, and other algorithms are good for locations next to the North Pole or next to the South Pole or next to the equator or something. So they differ on their locality, And there are some algorithms which work for the whole world, but they are then not so accurate as another algorithm which works only for this part of Germany, but they are more generic then. We will take a look at this very soon. When we talk about coordinate systems, and we go back to this example here, which has nothing to do with the Earth, then we can also say, I said maybe this is a CPU, then this is 0, 0, 1, 0, 0, 1, 1, 1. So simply coordinates on that CPU. Or this is a room, 0, 0, 1, 1, and so on. So within a building or a room, you can also have a coordinate system. So 3 kinds of coordinate system. One which is really related to our globe, then a projected one. We can use the very same units if we want, because we are still talking about the same Earth. Or for not related to Earth surfaces, we can use abstract coordinate systems, X and Y coordinates, or X, Y, Z, when we have a 3-dimensional space, location on an image, for example, location within a building, within a campus, or a chess field, or CPU, whatever. Yeah, in the chat, somebody mentioned the Mercato projection. This is one algorithm which works for the whole world. Where did you use this? Have you already worked with such a Mercato projection, just such an algorithm? Where did you use this already? In another lecture or in a project? Tell me in the chat. We can talk about that later, because the next slide will be exactly about these coordinate systems. We call them spatial reference systems, and a reference system, is used for projection, projecting something on this on the Earth to a flat surface, to a flat map. The most important ones are maybe 4326 and 3857, because they are used for the whole world. And I added some more which are very good when you work with German coordinates, because they are very accurate when you are exactly within this coordinates here. So when you try to translate something, a point in New York, into that coordinate system, you will get an error, because it is very limited to only a part of the German area. But these two work on the whole world. We will use some of those reference systems today. So reference systems are locally, regionally, or globally systems to locate geographical entities. When you want to compute the distance between New York and Germany, this cannot help you. This here could, but it uses the unit of degrees. Then you have the distance in degrees. And this one here, which maps the coordinates into into such a pseudo Mercator system, uses the unit of meters. So here we have X and Y coordinates, but not in 0 to 90 degrees north, south, 180 west and east anymore, but we now have meters here. And this mapping is really useful for calculating distances. There you can say, give me the distance between 2 points. And what we often have to do is to translate to translate between these reference systems. So I gave you already the answer, but do you remember it when? No, sorry, this is something new. Yeah, what would you say? We are using, so go to frage.de, we are using SRID 4326. What's the distance between London and Tokyo? I just made up 4 values. Choose the one which is more plausible for you. The Mercato projection was taught in, what is THD? Darmstadt, Deggendorf. No, Darmstadt doesn't have a Technische Hochschule. Deggendorf, yes. Okay. So the distance between London and Tokyo. So Google Maps doesn't show me the distance, just the length of the flight. When I go with the car or the bike, it cannot. Here. 8,000 miles. I have to swim, I guess, and it takes me 24 hours. It has a day, so 100 days. Oh, it's okay. 8,000 miles could be, yeah. So I give you the solution. The right answer is 140 because it's 140 degrees from London and Tokyo. So London is here in Great Britain. It has the longitude 0, and let's say Tokyo is at the similar latitude. It's a bit south, so yeah, but it's almost at the other side of the earth, so almost 180 degrees. 140 is the correct solution here. I can later show you a query in SQL how I found this out. It's not 15. Why 15? I don't know. And this is maybe the distance in kilometers or so, but no, the SRID uses the unit of degrees. So let's come to SQL now, and in SQL there is a geometry data type. So in the SQL spatial standard, they call it ST geometry, and they have many other subtypes, but we will use PostgreSQL today. And in PostgreSQL, first of all, in PostgreSQL there is no geometry data type, but in PostGIS, this is an extension, very popular one, which you can install and enable. And when you enable this extension, you have access to the geometry data type. And in PostGIS, there's only geometry. Geometry is used for geometric objects in general, for surfaces, curves, points, collection of multiple points, curves, surfaces, and so on. Curve polygon, polygons, line strings, and so on. And the SQL, we will take a look at these data types and subdata types in a minute. And the SQL spatial standard consists of routines to work with these objects. So let's take, for example, ST point. That's the easiest one. That's a zero-dimensional data structure. It just has an X and Y coordinate. A line consists of multiple points, a line string. So a line consists of 2 points, and a line string in general consists of 2 or more points. It can be a closed line or just a line like a river and so on. And we have methods, for example, which tell us true or false if 2 geometric objects are the very same. So for 2 points, this is the case when those 2 points have the very same coordinates. For 2 line strings is when they perfectly overlap. So not only if they consist of the very same points, but maybe they consist of different points, but it is nevertheless the same line string. So if it's perfectly overlapping, then 2 geographical objects equal. 2 objects intersect each other when they intersect each other. So we can, for example, have such a polygon. A polygon is a surface, an area which consists of lines as their borders. Polygons can also have holes in it. We will take a look at this in a minute, but this is a very easy polygon, and I could now draw a second polygon, or I draw a line string, so something like this, and intersects, true or false. Yes, this polygon and this line string intersect, and you can now imagine in your head something that does not intersect. This polygon and this point does not intersect. If the point would be in the polygon or at the border, then yes, so that's intersection. Intersection, so intersects gives you a Boolean, yes or no. Intersection gives you a new geometric object that forms the intersection. So for intersection between this polygon and this line string, it would return that line string here. So you can compute then a new object which is a line string, the line string here. stBuffer is my favorite function. It takes a geometric object and a distance. I come to this function in a minute. Then it's easier because I have also a picture about that. I can give you an example. This object here and a buffer of 50 kilometers would be a circle with a radius 50 kilometers. This line string and a buffer of 50 kilometers would give you such a area. So it produces a new geometrical object which is in all directions 50 kilometers larger. And why is this my favorite function? Why is this useful? Tell me in the chat, why do I like the buffer function so much? For this polygon, it would compute also something around the polygon also. It produces a buffer. This works for all geometric objects. Why can this be useful? You can get a distance? No, because the distance is provided in the buffer function. I have to provide the distance. I say this point, comma, 50 kilometers. Something collision. Yeah, if this is a plane and this is a tower or so, is object B in distance of C or D? Yes. That's the point. That's a very a point. Is an object closer to 50 kilometers from another object or so. Because sometimes the real distance between this line and this dot is not so important. So let's say this line here is how a plane flies. This is an airline. No, airlines don't go like this. Let's say it is a train connection. The train goes from here to here, or a highway from cars. Doesn't matter. A street or some transport. And I want to find all customers which live 50 kilometers or closer to that line, to that track, to that street, whatever it is. So I compute a buffer, and then I check with the this would be possible with the intersect function, intersects, but usually you use within. So is this point within this this area, yes or no? So intersects is very generic. It computes if two objects intersect, and this within has specific properties, that the dimension of the one object must be one higher than the other. So we can no, that's not true. Must be higher, not one higher. But an area cannot be within an area. But a point can be in that area, or a line. Useful when planning streets, you have a certain distance to be away from nature sites, exactly. So you do not want to calculate, you do not want to know the distance is given, and you want to find objects that have this distance. And it would be much too costly to compute the distance, because distance computations is very complex. Computing the distance between this line string and this dot is possible, and it is not cheap, but it's provided with the distance function. It makes a 90 degrees here, and the shortest distance is it basically. So the distance between this dot and that dot is very easy, Pythagoras. But the distance between a multidimensional object, like a line or an area, is the shortest distance between the two objects. So this area and this area, then this is the distance. So it is complex to calculate. And let's imagine you have 1 million houses here, and you want to compute which are the houses that are 50 kilometers or closer to that highway here. Then you have to make this distance computation 1 million times. And using this buffer is much more efficient. Yeah. Then we have something like STX. It gives us for a point the x coordinate. ST area gives us square meters or square miles, square degrees, so the area of a surface. Yeah, we come to those functions in a minute. So let's begin with the zero-dimensional geometries with a point. Zero dimension means it is just one point. So there's the data type st point for that. This here is the so-called WKT syntax. It stands for well-known text. So there are multiple ways to define a point or a line string, or for all data types here we have the WKT syntax to define it. And in SQL this is very convenient, because there are constructors which take a WKT string and construct a geometric object. They take such a 0.55 and give you back a geometric object. You cannot do a lot of things with that. You can then call functions or store it in a geometry column, or convert it maybe back into a WKT so that you can read it as a varchar as a string. Yeah, there are other formats as well. There is, for example, well-known binary, WKB. There are also constructors which take an WKB. This is then not in text format. Text is very nice for humans. We can quickly read it. WKB, well-known binary, is 00110001100 binary format. More compact, but not made for humans, but for machines. Multipoint is a subclass of this stgeom collection. So it is used for, it is basically a set of points, or a multi-set of points. They can overlap. So a set of points. Routines to work for points. I call it routines and not functions because it is different in each relational database system how they implemented the standard. So the word routines is a term which combines functions, procedures, and methods. Function is, for example, uppercase. Uppercase hello is hello, so in uppercase letters. The procedure truncate all tables is a procedure that does something. It truncates all tables, but it doesn't return anything. Procedures can return dynamic result sets and so on, but a function really returns one value of a specific data type. Routines do not. Procedures they are void, and methods they have access to this. So a method has a this, or in SQL they call it self. You call methods on a specific object, like in a object-oriented programming language. In Java, you say my point dot get x or something. You call the method get x to get the x coordinate of a point. Yeah, and this is how for example, DB2 implemented the SQL standard. In the SQL standard, they say these functions are, these routines are methods. So not like I wrote here, stx of a given point, but you would write it, you have a point, P, and then you write stx and no parameters. So in DB2, you would get the x coordinate of a given point with a method syntax. Actually, in DB2, you need to write 2 dots. And in PostgreSQL, they implemented everything as functions. So they take the geometric object as parameters. So and I am using the PostgreSQL syntax here. So also on the slide before, you can imagine how this looks in DB2. So st equals only takes the second geometric object and it's called on g1 dot dot st equals and so on. Yeah, so that's why I call it routines and not functions. But in PostgreSQL, they are functions. Yeah, and there are not so many functions for points. These are specific functions for points. Of course, there are many functions for points because there are many functions which work on any geometric, but these are only possible for points, x and y coordinate. Yeah, and for multi-points and other geometric collections, you can iterate over them. You can get the number of points in such a multi-point. So it would return 3 here. You can say, give me the first point, the second and the third point, and so on. One-dimensional geometries are, for example, lines or line strings. Actually, there is not a type line because they simply say a line is a line string of length 2. So a line string is represented by a sequence of points. So the order is important, and yeah, you define in this case here 3 points: 1 1, 1 3, 3 3, and the line are all interpolated points between them. So that's a line string. This is also a line string, and this is called a closed line string when the last point, the end point, is the same as the start point. Then we call it a closed one. Yeah, it is closed. You can ask, is it closed, yes or no? With the is closed routine, you can compute the length. So that's basically the distance between the first point and the second point, plus the distance from the second to the third, and then and so on, yeah, to the last point. And for a closed one, the last point is again the first point. So this distance would be this plus that plus that. Point n gives you access to the nth point. So point n of this line string 1 gives us this point, 2, 3, 4. I don't know if they start counting with 0 or 1. Number of points, n points of this line string, start point and end point is basically this point n, but for only getting the first or last point on that line string. So line strings can, for example, be a route, go there and then there and then there, or a river, the river goes like this, or if you take a run, you go in the park, or you have a ride with your bike, and then maybe this is a closed line string because your trip ends at the very same point where you started, and so on. So then you can compute the distance and so on. Two-dimensional geometries are in general called surfaces. We will only focus on polygons here. Polygons are very easy because they are basically closed line strings. So when we have such a line string here, you can also write, so this would not be possible when you write polygon here, but if you would write polygon here, then simply imagine that this would be filled red. So it is a line string, a closed line string is also a polygon. You can convert it directly by using the same syntax into a polygon. Other surfaces would be something which is not a line string. So this is very curly, and yeah, we will not focus on that. Line strings are much easier. It is possible to have such so-called curves. So a curve is defined by a dot and another dot, and then a third dot which says how where the curves should go. For example, this dot would define that the curve should go like this, and then the curve consists of 2 more dots. Maybe here's one, and then here it would then make this curve. So then every possible curve and then every possible curve polygon would be possible with that. But we will focus simply on line strings which are very linear and yeah, not curvy. Yeah. You can ask for a start point for a curve. That's what we had. For polygon, you define them by, first of all, a line string which defines the outer border of that polygon. And polygons can have holes. So this one here has a hole. You see the first part of this polygon is exactly the same as this one here. 0, 0, 1, 1, 2, 0, 1, minus 1, and again 0, 0. It's a closed line string that defines the outer border. And we used here a second closed line string to define that first hole here. Yeah. And with this, all kinds of polygons are defined. You can define much more holes here if you want. And when I go back to the hierarchy, to the type hierarchy, there in the geometric collection, I just wrote ... Here is multi-polygon, multi-point, multi-line string, and so on. Write me in the chat, what would you say is the geometric data type? So here's again the, oh, it's not complete, so I don't show this slide. What's the geometric data type for a country? Germany, USA. What's the data type of a country? Can you write this in the chat, please? And then we come to the next quiz question. What is a country? ST Polygon. I show Italy, and Italy is not a polygon. It looks like a polygon, blah, 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 but this here also belongs to Italy. And that's the reason why a country is not a polygon, but exactly a multi-polygon. So when we import countries, you do this in the exercise, then we have multi-polygons. And you can simply then ask, does a multi-polygon contain the following point or line or whatever? So now another question. What's true for the two polygons on this slide here, this polygon and that polygon? There are routines like computing the area in square degrees, square meters, depends on the SRID that you use. The parameter, so this plus that, so basically the length of the line string of the outer border, and the centroid gives you a point, yeah, where you can balance the polygon. So where is the centroid, the middle of the polygon? Yeah. What's true for these two polygons? Same area, same centroid, same area, different centroid, different area, same centroid, and different area, different centroid. Okay. Yeah, the area is of course not the same. Here's more red. The parameter is, no, the centroid is the same. Exactly. I just opened dbeaver, and dbeaver is my favorite client for working with geometric data because it can visualize the results on OpenStreetMap, on a map. You can install Postgres. You have to install Postgres when you work with geometric data, but on this Hera server it's already installed. And one so all functions start with st, and there is geom from, here you see from WKB, WKT, from GeoHash, from GeoJSON, so many constructors to generate a geometric object. This from text is the same as from well-known text, so I use this stgeom from text, and then you can provide such a WKT, so for example this 0.55 or so, and now you can, yeah, this is the point. Yeah, it's not very interesting, but I can, for example, take this polygon here, and it draws me that polygon. It tries to show it on a map, but this does not belong to a coordinate system. No spatial reference system is used here, so it shows me this polygon, and we can then, for example, also have the other polygon where no hole was in it, and then with control click we have both here, and now I can, for example, calculate the area. Select ST area of this and the ST area of that. So the area is smaller for the one with the hole as for the other, and from the ST centroid, or I don't know whether PostgreSQL implemented this. Yes, yeah, it is the same. Rounding errors can occur, so you see here it is 1 0 minus 0. Okay, the centroid returns the point 1 to the right and 0 to the top, so that's the centroid, and it is the same. Yeah, here are some other routines, and here's also a picture of it's a very simple version of the river Rhine. I simply chose one point where the Rhine has its origin, and the no, here is the origin, and here's the where it goes into the sea, and then another point, Bingen am Rhein, I chose, and then it's simply a very simple version of the Rhine. It's not correct, and then I computed a buffer. This buffer of, I don't remember how large it was, 50 kilometers or so. So to find all cities or so within a radius of 50 kilometers of the Rhine. Good luck balancing the one with the hole. Yeah, balancing is then very complicated. There are routines for all geometries. Envelope is the bounding rectangle. So when we have our, let's say this is a geometric collection of everything, then the bounding rectangle, the envelope would be the minimum rectangle where everything is in. Then the buffer, yeah, encircles the geometric at a specific distance. We saw here. We can compute minus, so the difference, so we can subtract one area from another, for example. We can intersect them, unify two geometric objects, so they all return geometry again. Then predicates, which return Boolean, so if they intersect, if they cross, if they overlap, if they just touch at the borders, if they contain each other fully, or if some object is within another object. So basically contains and within is the same, but you provide them in the different order. So G1 contains G2 is the case when G2 is within G1. Yeah. And there's a function is simple if it does not intersect with itself. So line string is simple. All line strings that we already had are simple, but if they are intersecting with themselves, then it's not simple. Okay, in PostGIS, we now have the geometry type. We install PostgreSQL and we install PostGIS. PostGIS, you can find it on the website. You have to download it, install it, and then fire a few commands after installation to enable it. So introduction, then installation, blah blah blah, install. And yeah, I used PostGIS Ubuntu, and there I had to here fire these commands as well. Create extension PostGIS, and this is sufficient. So you don't need these other extensions, fuzzy, string match, address standardizer, and so on. So there are much more extensions. The PostGIS is the one that we need. This provides us the geometry type and the functions st something. Isn't Postgres included by default? No. PostGIS is not included by default. You can say geometry when you create a table. I think this is possible. Create table drop me x geometry. It is possible. Then you can store any geometric object in there. It's better to provide the information what kind of geometry you want to store there. For example, geometry point allows you only to store points. So here we have a table buildings. Peter lives here, and this here is a point, and we provide the coordinate system reference. So this is the SRID of the coordinate system, which uses longitude and latitude, which makes it easy to insert his position. So we insert two people, Rita, and use this stgeom from text to insert the position of Rita and the position of Mary. So we insert two people, and then we can use our functions that we saw on the previous slides. For example, the distance between r.geo and w.geo. And R is one table where we say one row where we say customer name equals Rita, and W is one row in the buildings table where we say customer name is Mary, and then we can compute how many kilometers, because this is in meters, and when I divide it by 1,000, how many kilometers are Rita and Mary far away from each other. If I would not, so I can now reproduce this here, and if I would not use this transform, so let's say I create the table buildings, insert two rows here, Rita and Mary, I can simply say select star from buildings to simply take a look on the map where Rita lives. She lives there, and Mary lives there. So we have two dots here. And then I can use this query to compute the distance. 578 kilometers. So what was it? Rita, I think, lives in Regensburg. You can also press here, open in browser, then it's bigger. Then it opens OpenStreetMap on the browser. So here's Rita in Regensburg, and here Mary in a town called Mayen next to Koblenz. and you can compute the distance between Mayen and Regensburg. Google Maps is not good for distance because this is the real Autobahn distance. So 464 kilometers. So the real distance should be smaller, but PostgreSQL says it's 578. So it's not very accurate. Yeah, that's something must be careful with. The distances that you compute here are not very accurate. Maybe another SRID would give you a better distance here, because this 3857 is the one that I had for the whole world. And as I said, these are much more accurate, but they work only in a part of German, so it would not be possible, I think, to use one of those here. It works, and it gives us a much better value here. So this is much better. It only works in Germany, but gives us a more accurate result. Yeah, and both are in meters. So that's why I do this transformation. I transform Rita's position into a map which uses meters and not degrees anymore. I use in the table this unit to support all points on Earth in degrees, so that I can insert it in that format here with the degrees. And I transform it into another system which uses meters because I want to know the meters. For many functions, like does something overlap, is this within a country, does these lines cross, and so on, it's not necessary to transform something from one reference system into another, except when you import two data sets from different sources where they use different SRIDs. But when you have them in the database, you typically do not need to transform them anymore, except when you want to know something in meters or something is given in meters, like we did here. And if I would not transform it, so I would simply say, what's the distance between r.geo and w.geo, then this is the distance in degrees. So the distance between these two people is 5 degrees. And that's the formula which I also used for Tokyo to London from the other slide. Yeah, and on the next slides, I'm using a bigger example which I have from a very nice paper. It's a paper that that's about this SQL spatial standard. You can read everything about that standard in this very short, compact paper. For example, ST, it stands for spatio-temporal, so it was originally thought for geometric data and temporal data, but in the end the temporal part was done a bit different, so it now stands for spatial type or something. These are some facts out of this paper. It is a paper which simply describes what this SQL spatial standard is about. It's a standard to manage spatial data in a relational database system from some years ago, and it uses a very nice example which I really liked, so I used this example here. We create a table rivers. That's the table that's the river which I already had here on this slide, and I insert in this river table just for testing one single river, the river Rhine. We could make it very accurate by defining this river by as much points as possible where the river Rhine goes. I simply use only 3 points. So here it starts in Switzerland, I think, in the Alps, And then here is a city, Bingen, next to Mainz in Rhineland-Palatinate. And then here's a location next to the sea where it ends. So this is the river Rhine, just consisting of 3 points. And the same as before, I use the geom from text function as a constructor. This is basically my constructor. I give it in varchar as a string, and I get a geometric object, a line string. Yeah, and this is what I call what I insert here. River Rhine has river line has the type geometry line string. So let's create it. So my table rivers is there, and I insert the river Rhine. Select star from rivers, and dbeaver is also able to visualize all geometric data. So here we have our river. It's very very bad approximation. So I think Bad Münstereifel is not next to the river Rhine in reality. So we would need more points here, but just for demonstration. Okay, then I have another column called flood zones, which currently is just null. And that's often done for making computations faster. We materialize something into another column. This makes queries simpler because I want to find out which customers, we have our buildings table from before, which buildings are 5 kilometers or closer from the river Rhine. So for an insurance company, these customers must have a higher insurance cost because they are more risk. They have a higher risk that they have a flood in their house. So the insurance company wants to find out which of my customers live next to the river Rhine with 5 kilometers. Oh, 3 kilometers here. 3. So update rivers, set flood zones equals blah blah blah. So I go into my rivers table, and for each river I find there, I take a look in the river line. So I find this line. First of all, I transform it into a metric format again. And this way I can say to the buffer function, I want 3 kilometers buffer. If I would not transform it, I would have to provide the buffer in degrees. And the degrees here is maybe different than here. So it's important to use this projection to project it to a map which uses meters. And then I say compute the buffer here. And then transform it back into 4326 because multiple reasons. The main reason is because my flood zones data, because my flood zones column needs this. So that's the main reason. If I would not transform it here in the end, then it would say, this is always a warning by dbeaver when you have update queries without a where clause. So geometry SRID 3857 does not match the column with which has SRID 4326. So I have to transform it here again. And the other reason is, so I could also say that this data type here would be geometry of the 3857 geometry, but I would not recommend to mix it in your tables. This only gives you problems, and when we later want to find who are the people, who are the buildings that are within this flood zone, and for the buildings table we use 4326, and for the flood zones you use that. Please unify it and make everything the same, the same SRID here. So I transform it back, And now, after the update is completed, I can take a look in the rivers table again. So here we have Polygon. Yeah, it looks like a line string because 3 kilometers is not very much, but you see here when I zoom in that this is now a polygon. Actually, it's not a polygon, it's a yeah, it's a really nice surface because here it is round. Yeah, because I think the last, let's visualize both the line string and the buffer, the line string of the river and the flood zone. There you see that here at the end it's yeah, it's this rounding here. So it's when somebody lives in this flood zone, you can say that the distance between that building and that river is 3 kilometers or less. And that's what we do now. Find all customers that have a building. Find all customers that have a building in the flood zone. And basically this is a geometric join. So it does not look like a join. From buildings B, rivers R, where the building is within the flood zone. But actually this is a join. If you want, we can also use this join on syntax here. So Mary, yeah, wow. Let's make star. So we have Mary who lives here in Mayen, and then the river. You already see that this is very close. It's not exactly on the line. This would be almost impossible. But within the flood zone it is. Yes. And Rita, who lives in Regensburg, is not found here because Rita was in Regensburg, and that's definitely not in the buffer that we computed here. So this is a geographical join, like a join predicate where x.a equals y.a or something. You can say buildings B join rivers R on. This is exactly the same query. Yeah, a geographical join using some function which returns a boolean to check whether a row in this table has a join partner with a row in that table or not. And a building has a join partner with our river if this building is within the flood zone, within the 3 kilometers of the river. And these are typical queries. Find something next to another object. So find people who live in Frankfurt, or who have a distance of Frankfurt 50 kilometers or less. Many people would do it like this. Take Frankfurt and then every customer, and then where distance less than 50,000. But that is costly. It would be a better idea to take the point Frankfurt, compute a buffer with 50 kilometers, and then where the building, where the customer is within this buffer. We can do it later when we have more time, but I think we are almost running out of time. But I will do one more example when I talk about geoindexes. And in geoindexes, this is a feature which is not part of the SQL standard. SQL standard never talks about indexes, never talks about performance. SQL standard only talks about the language and its features. The indexes is something the relational databases have to build on top, because they want that it works fast. And imagine that you have 10 million customers with 10 million buildings, and you have thousands of rivers, then this query would be extremely expensive when you have a nested loop join where you have to compute every building, compare every building with every other river. And especially these functions, geometric functions, are expensive. So this would be very, very slow. That's why there is a need for geoindexes. I will not go into detail how they work, how this R3 structure, which is one and the most popular one for the geoindexes, work, but I just want to give you a very short idea how they work. So it is a tree structure, like a B tree. It's balanced. You always have the same distance between the root node and every leaf node in that tree. And when you search something, you go from the root deeper and deeper that matches your criteria. And in each node of that tree, you have a rectangle. So a rectangle is basically 2 points. This point and that point, that's a rectangle. A rectangle is defined by the point of the upper left corner and the lower right corner. And the R3 stores in its inner nodes rectangles, and in the leaves the objects that we want to store. So let's say this is the River Rhine. This is a point where a customer lives, blah, blah, blah. And the algorithm, when inserting something into an R3, looks where should it be inserted. And we produce bounding boxes. So we have the objects R8, R9, and R10 here. They are close to each other. Say 8, 9, 10, they are close to each other. So we create a minimum bounding box. So we have to find close nearby objects and make a bounding box. And then this bounding box which we create, it's not an object that's stored in the database. Only the red objects are stored in the database, only the leaves. This bounding box is something we compute, and this is written as a way indicator within our inner node. So these objects have a rectangle, upper left corner, lower right corner, and this here has a rectangle. And when we now want to find something in the tree, give me something that is in this rectangle, blah, 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 then we navigate through the tree to find overlapping rectangles, because when it overlaps to our search query, then it can be there. For example, let's say we have one rectangle 10, 100, 105, so it's a rectangle from 10, 100 and 105, and then we have 0, 50 and 170, 0, and we want to find in this rectangle here. And when in the root node there is one which does not overlap with our search. For example, this rectangle 1 does not overlap with that one. You now have to imagine this in your head, how so 10, 100 and then 105. So it is far away from that other rectangle. They do not overlap, so it's not necessary to search in this part of the tree. So these objects you do not need to compare. The customer will not be in the flood zone of these rivers, or the river does not have a flood zone where these customers are in, depending on what you indice. You only have to focus on these here. And this goes hierarchically to limit your search space. So it makes searching for containment in the geodata much easier. And in PostgreSQL you can create such a geo-index by using gist. So it is a normal create index command, but you don't say using btree or using hash, you say using gist. Gist is also used when you want to index JSON data, so it is the same syntax here. So when we create such a index here, for example, our query find all buildings, so it is a new query now. I take the point Regensburg, find all buildings within 10 kilometer radius of Regensburg. So please don't say where distance of this point here and the geo coordinates of a building is less than 10 kilometers. First of all, this uses always a nested loop join. It can never use an index and is expensive in any way. So don't use where distance less than 10. Take this coordinate, the point Regensburg, compute a buffer. So this is now a circle around the city Regensburg with a radius of 10 kilometers, and then say give me everything that's within this circle, and this can use the index. So let's make here this query. Oh, I copied too much. So yeah, it finds Mary, but let's for testing just return what we provide here. Select this polygon. Yeah, so we have this point here, then we convert it to the meter SRID, then I make a radius of 10 kilometers, and then I transform, so I make a buffer of 10 kilometers, and then I convert it back, so it returns me a radius around Mayen. Aha, why is here Mayen? It says from Regensburg, so I cheated here. This is not correct. This should be Regensburg location. So wiki Regensburg, I had this here. The coordinates can be in many different formats, so degrees and seconds and minutes and so on. Here this is what we need, just a decimal format. And we need it in the other direction, so we first need latitude, first need longitude, this 12 blah, and then latitude. So now we have the buffer around Regensburg, and now I can compute who lives within that buffer. And when I take the analysis of this query, it uses a sequential scan. It checks for every customer, is it within this geo coordinates, yes or no. When I now create an index on this geo column, let's do it. Create index on buildings using gist, and the column is called geo. Then the index is there. And as you can see, it now uses the index. I forgot. Test. My charging cable was not connected anymore. And I hope you can hear me again. Don't know. Can you still hear me? But we are anyway almost at the end. I had to connect my charging cable properly. Yeah, that was the idea of geo-indexes. So again, I can, for comparison, drop this index, drop index File GeoIndex is, I think, the default name. And then look, it uses the index and it costs 51, and with the index it costs only 33. And for bigger data, of course, the index is absolutely worth it. Okay, that's the end of today's talk about geodata. What we saw was geoinformation systems. We took a look at different coordinate systems which use different units and are made for different locations on the world. We needed to convert from one system to another, and the SQL spatial standard has data types like stPoint, stLineString, stPolygon. Postgres only uses geometry, and then you specify what kind of geometry do you want to store. And the SQL spatial standard offers routines to work with this data. We took a look at the WKT, the well-known text format to define, to construct such elements. And and in the end, we took a look at geoindexes, which are used to make efficient queries on geodata. Not every function can use the geoindex. For example, when you say what's the distance between this and that point or a geometric object, therefore you cannot use a geoindex. But for things like, is this within that, then you can then the geoindex can be used. You can imagine, when you take a deeper look at how an R tree works, which kind of operation works how would you implement a within query when you have your data in an R tree. I navigate through to the rectangle, which is the bounding rectangle around this object, and then I search for all objects within, and then I have to check again if it's really inside or not, because the R tree is only having rectangles, and when something is within a bounding rectangle, it may be in the other geometric structure. So it gives you a first hint, it boosts a lot of the performance, but in the end you have to again compute if it's really within that area and so on. Okay, do you have questions about geometric data analytics, about spatial data? Then have a nice day and see you next time. Goodbye.